Let us now apply the de Moivre-Laplace theorem to derive an interesting formula. It is usually called the formula of the size of the representative sample. So imagine the situation that you are working for a political party, and so you want to perform a poll, a survey, and so an electoral survey. You want to know the proportion of voters that support your party, that will vote for your party in the elections. So what do? You just go out to the street and you ask random people, and you just ask them, will you vote for our party? And let's simplify the situation. Let's say that everyone just answers yes or no. And then you divide the number of those who answered yes, who said yes, by the total number of people you asked. And so this proportion is your estimator of the real proportion of the voters that are in favor of your parties, that will support your party, that will vote for it. So, and the problem is how many people you should ask. So how many is enough? If you ask 100 people, it is enough, or it's better to ask 200, or 300, or 1,000, or 5,000. So how much is enough? So we understand just by our intuition that the better you ask, the more accurate the result will be. So if you ask just 2 people, and let's say that both are supporters of your party, then you'll get 100% as a result of your poll. And so this will probably have nothing in common with the reality. But so it's better to ask as many people as possible, but this can be very expensive. So you can ask millions of voters, but this is very expensive. You should have many employees who will do this survey, so who will work with the results and so on. So it's better to find some optimal number that is not too high, so that the survey, so you don't want the survey be too expensive, but still you want the results, your estimation of the real proportion of supporters of your party to be accurate. So what should we do? So the first step is to define the accuracy you want to get. So you can say that I want, it is acceptable for me that difference between the real proportion of voters who support my party and what I get as a result of my survey, so difference between these two proportions. For example, if the difference is no more than 2%, this is acceptable for me. So this is accuracy of your estimation. So the first step for you is to say what accuracy is acceptable for you. You can say 1% or 2% or 5%, or it's better to express it not in percents but in decimal numbers. So let's say that the delta is accuracy. Accuracy means maximal error, maximal difference that is acceptable. that is acceptable for you. Then, even if this delta is given, so you say, let us say 5% accuracy of 5% is enough for me. But still, as you choose these people for your poll, it's random. So these are random people. And so this difference, this error, can be more than 5%, just at random. You cannot guarantee so that the difference will be less than 5%. So you can choose, you can ask very many people, several millions people, but you cannot guarantee that the difference will be less than 5%. Probability of difference being more than 5% decreases when the sample size increases. But still, this cannot be guaranteed. So the second value you are to choose yourself is probability that the error will be more than delta. And we usually use letter alpha for this. So alpha is the probability that the error is greater than delta. So you say, for example, I want the error to be less than 5% with probability 0.99. This means that alpha is 0.01. So if you want the error to be no more than 5% with probability 0.99, that means that you agree that with probability 0.01, the error will be more than 5%. This value is the alpha. So these are two values that you must choose yourself before just dealing with this problem. So you should define the accuracy and the probability that the error will be more than the chosen delta. Now, we should introduce some other letters for the proper notation. Let us say that P is real proportion of people who are supporters of your party. So this is real proportion, or they say in statistics, they usually say population proportion. So proportion of these people in the whole population. Population proportion is non-random, but it is unknown. It is non-random and it is unknown. N is the number of people you are going to ask. So N is the sample size. The sample size. M is number of people who tell you that they will vote for your party. So we can interpret what is happening here as a series of Bernoulli trials. So when you ask a person, will you vote for our party? This is a Bernoulli trial, and when this person tells you, yes, I will, so this means a success. So we can say that M is the number of successes. M is number of successes, and P hat is what you get by division of M by N. So you divide number of those who are in favor of your party by the number of those who took part in your survey. And so this is usually called a sample proportion. So this is the sample proportion. And so the sample proportion is your way to estimate a known population proportion. So this is our notation. So we will use these 6 letters: delta, alpha, P, N, M, and P hat. And so now what do we want? We want to choose N such that difference between P and P hat, between population proportion and the sample proportion. So we want the difference to be no more than delta with probability alpha. So we want that probability, we want for the probability that absolute difference between P hat and P being more, let's say being less than delta, being equal to 1 minus alpha. So we want to choose such N that will guarantee this equality. So that probability, that difference between what we get after our survey and what is the true proportion, the population proportion, the difference between the sample proportion and the population proportion. So probability that the difference is less than delta, so less than this threshold that we that is acceptable for us, must be equal to 1 minus alpha. So alpha is the number, is the probability close to 0, like 0.05, 0.01, and so on. 1 minus alpha is the probability close to 1, big probability. So we want to guarantee with big probability close to 1 that difference between what we get and what is in real life is less than delta. So this is our aim. And now let's try to see how can we find N according to this condition. So we now know that we want to choose our N to guarantee this equality. Okay, so here we see that delta is non-random, alpha is non-random. So delta and alpha are both chosen by ourselves, and so but this is a random variable. P hat is a random variable. Actually, P is also non-random, but let's consider this P hat minus P as a single random variable, and I'm interested in its distribution, in the distribution law of this random variable, P hat minus P. So let us start with P. Actually, P hat is M over N, and let us start with M. So M is a number of successes in a series of Bernoulli trials. So M is number of people who tell us that they will vote for our party. So M is a random variable that has binomial distribution with parameters N and P. If we deal with the number of successes in a series of Bernoulli trials, So that is why the distribution is binomial. Okay, but we know that according to the De Moivre-Laplace theorem, we can replace binomial distribution with the normal one if the number of trials is big enough. And here we know that big means more than several dozens, and we know that if we want to make an electoral poll, so this n will be big enough to apply this theorem. So we can say that as n is big, it can be assumed that what? That M has normal distribution with parameters np and n times p times 1 minus p. Okay, so then, and p hat is m divided by n. So p hat is m over n. So what about the distribution of p hat? We see that so n is non-random. N is unknown but non-random. We will choose n ourselves. So that means that p hat is a normally distributed random variable divided by a non-random number. And so this does not change the type of distribution if the distribution is normal. So we know that linear function of a normally distributed random variable is also a normally distributed random variable. So this division by a non-random number does not affect the normal distribution. So that is why p hat is also normally distributed. And if we consider not the p hat itself, but p hat minus p, it will be also normally distributed for the same reason. So as p hat minus p is equal to m over n minus p. So n is non-random, p is non-random, only m is random. M can be treated as a normally distributed random variable. So this is linear function of m. This is linear function of m, and so that is why the distribution of this random variable is also normal. And we are to find the parameters. And the parameters are expected value, the expected value and the variance. And so the expected value of p hat minus p is the expected value of m over n minus p, and this is 1 over n times the expected value of m minus p. So this is, and the expected value of m is np. So this is 1 over n times np minus p. That is 0. So expected value of p hat minus p is 0. So the first parameter is 0. Then, as for the variance, what do we have for variance? For variance, we have so that this is variance of m minus n or m over n minus p. Minus p, this subtraction does not affect the variance, as we know that if we add or subtract a non-random number from the random variable, it does not affect the variance. And this coefficient, 1 over n, is squared when put out of the variance. So this is 1 over n squared times variance of m. So we just used standard properties of variance here. And variance of m is n times p times 1 minus p. So this is 1 over n squared times n times p times 1 minus p. that is p times 1 minus p over n. So this is the variance. So the second parameter here is p times 1 minus p over n. After the distribution is known, and we know that the distribution is normal and we know the parameters, we can apply this to find the probability. This probability, to express this probability with the in a standard way we use for normally distributed random variables. So I can say that the probability of our interest, probability that difference between p and p hat is less than delta. So the first step is to open this modulus. So I can say that this means that it is from minus delta, that p hat minus p is from minus delta to plus delta. And now I say that as this random variable, p hat minus p, is normal with these parameters, this probability is equal to phi of delta minus mu, that is 0, divided by the square root of variance, divided by square root of p times 1 minus p divided by n, minus phi of minus delta minus 0 divided by this. So, as you see, the only difference of arguments of phi here and here is the sign. So the sign is different. And the phi function has such a property that phi of minus x is 1 minus phi of x. So, and let me now apply this formula. So I'll get that this is equal to, and I will also simplify this a little bit. So I'll say that this is phi of square root of n times delta divided by square root of p times 1 minus p. And so here, the argument of phi is the same but with minus of different sign, and I use this formula, and I say that this is 1 minus, so I get minus 1, minus times minus give me plus, plus phi of the same argument. So, this is 2 phi of square root of n times delta divided by square root of p times 1 minus p minus 1. So, this is how the probability of interest can be expressed, and you see that here we want this probability to be equal to 1 minus alpha. So I can say that this is to be equal to 1 minus alpha. So then in this, so this equality can be simplified as follows. So I can say that 2 times phi of square root of n times delta divided by 1 square root of p times 1 minus p is equal to 2 minus alpha. Or I can divide this by 2 divide both parts of this equality by 2, and so I'll get here 1, here 1, and this alpha will be divided by 2. So, and what is phi? Phi is the CDF of standard normal distribution. Phi is the CDF of normal distribution with parameters 0 and 1. And so, what is the point where the CDF is equal to a given number? This point is the quantile of this level. So as phi of this expression is equal to 1 minus alpha over 2, that means that this expression itself is the quantile of the standard normal distribution of the level 1 minus alpha over 2. So this means that square root of n times delta divided by square root of p times 1 minus p is the quantile. I will use z for the quantiles of the standard normal distribution, is the quantile of the level 1 minus alpha over 2. And so, from this expression, so from this equality, we can easily solve it for n. Our aim is to find n, so to find such n that this is true. So the only step left is to express n, to solve this for n, so it is very easy, and we will get this expression. So n is equal to z to the quantile divided by delta squared times p times 1 minus p. So, this is the answer. But if we think a little bit, we will see a big problem. What is the problem? So, we want to find n, we got the formula, but we see that n depends on p. And p is unknown. Actually, p is a population proportion, and all we do here, we do with the aim of estimating unknown p. So everything is done just to perform an experiment, to do a survey, to estimate unknown p. And here p is and we need p here to find n. So one may say, so this is an unsolvable problem, as we see that we need p to find n and we need n to estimate p. But p is a proportion. So p is a number between 0 and 1. And that means so that actually this product of p times 1 minus p, it can take only values between 0 and 0.25, between 0 and 1/4. So this expression takes its maximal possible value when p is 1/2. When p is 1/2, this is 1/2 times 1/2, 1/4. And for all other values of p, this is less than 1/4. So this can be easily proved. So you can say that, let's say that we have a function f of p is equal to p times 1 minus p, that is p minus p squared, and so derivative of f is 1 minus 2p, and if you equate this derivative to 0 and solve this for p, you'll get that p is 1/2. So this is the maximum point of this function. So the maximum of this function is when p is 1/2. So if you know nothing about p, if p is totally unknown, you can just substitute 1/2 for p here. You will overestimate n a little bit, But still, it is not so very big problem. So yes, you will ask a little bit more people than you need, that minimal number that is needed, but still you can find n. If you know something about p, so if you have results of some previous polls or something like this, so if you can imagine what values p can take, you can use these values and you can use the corrections. For example, if in previous poll p was 0.2, you can say, let us assume p being 0.3, a little bit closer to 1/2 than it was actually in previous survey. Maybe p has changed since then, and that is why you can to substitute value a little bit closer to 1/2 than the value that was observed sometimes. So it was observed in the past. So this is the formula of the size, formula for the size of the representative sample. So if you want to know how many people to ask, you apply this formula, you choose delta, you choose alpha, and you apply this formula, and so you substitute 1/2 for p if p is totally unknown, or you can use some previous information of some previous researches, of some previous surveys.